Hello everyone. I'm Marc-André Labonté. I'm here to talk about the Blackbear project, which is basically a fork of OpenSSH. I made that fork to transform OpenSSH in a reverse SSH shell. I was a system administrator for more than 10 years, and since 2 years ago, I moved away into penetration testing, and that is what I'm doing ever since. Why I did it, and I'm gonna talk about why I did it and how I did it, especially. It's a fork of OpenSSH. It's designed to provide a fully interactive shell. Don't know if you tried like the dev TCP bash trick or web shells or Python reverse shells. When you're using those shells, some command may not work properly, like top or vi or even sudo. So I wanted a regular SSH shell as a reverse shell when I need to do a connect back. And also, I wanted to leverage OpenSSH dynamic and port forwarding, like the SOX proxy, the VPN functionality, and the regular remote reverse port forwarding, and the regular port forwarding as well, which you won't have if you do dev TCP and bash. A bit of history about the project. It started when the Hackfest event used to have war games. The last two war games were playing countries fighting each other. And the first such war games, I was kicked out of my home machine by some adversary team. I thought, never again, so I started to fork OpenSSH to provide me with some sort of backdoor that I could use also defensively. So if some adversary in a war game will infiltrate my machine and change all the password and replace all the authorized key with my SSH fork SSH server, I will still be able to log in and fight back. And then the first version was based on OpenSSH, but it lacked the reverse shell functionality. Then I forked Dropbear, the Dropbear project. That's why it's called Blackbear. So the code base is simple, so I could understand the code and add the reverse shell functionality, but Dropbear do lack the SOX proxy for dynamic port forwarding, so I went back to OpenSSH. I became a better programmer, so I was able to finally understand OpenSSH and finish the job. So that's the functionality. Talk about it. Like you have to know that you could use these options to, let's say, you want to use an additional service on the target side. You will use the capital L option to open a port on your machine that if you connect to it, it will go through the SSH tunnel, then you will be able to reach the service on the remote machine. Because otherwise a firewall might prevent that connection. You may also provide services to the remote machine through your connection. Let's say you have a connect back, but from a network that doesn't have access to the internet, and you need machines from that network to have internet access. You can use the capital R option to open a port on the target side. If the target side connected, they will be forwarded to your machine, and then you can tunnel to a proxy and give internet access to the otherwise enclosed restricted network. So that these functionality, I wanted to have them inside my reverse shell. So of course, it's a post-exploitation tool, so you have to have the ability to run code on the target machine. So you have to have an exploit or a login or some way to run code remotely. And like I said, provides the tunneling ability, and I use it for manual enumeration. Like since I have a regular SSH shell, I can run VI, I can run top, I can run any tools that could be on the machine. I use it to manually explore machines. So yeah, I talked about that already. So fully interactive shell. All right. So the issues that I encountered in the development of the software, it's like I encountered what they call the privilege separation. Privilege separation is when the SSH server receives a connection, is gonna fork into two processes, and it's meant to provide security to prevent someone that is reaching the server from the network to reduce the attack surface. So what will happen is when you connect to the SSH server will fork, and then the network code will drop privilege. It will change route, so it will have restricted access to the file system, and then it will be further restricted with technology like seccomp on Linux or pledge on OpenBSD. That will restrict the system calls that can be made from that process, that restricted process. And another process will be created, that is the privilege one, and that privilege process will be responsible for authenticating the user. So it will receive the password or receive credential and the authentication tokens, or it will challenge if the user is using a key pair, will challenge the user to prove it has the required private key. And both processes do communicate with each other, more on that later. That could be abused as well. And also I did try not to use the disk on the target side. So I did want to bypass any account restriction. Let's say you are attacking a web server. The account the web server is running on often has its shell set to bin false or bin login, and there are also other configurations to restrict access to those system accounts. So I wanted to bypass that, and I wanted to leave as little log as possible. And I wanted not to depend on the target authentication mechanisms. So I don't use the target password databases. I don't use authorized key on the target. Actually, the authentication is done with a key pair, but the public key is embedded inside the binary. It's not on it's on the binary that you will upload, but not on the target server. And finally, I had this issue as when I do upload the SSHD binary to the target, I have to upload it, and then to toggle the execute bit on the binary, like do change mod on it, and then to run it with proper arguments. So I wanted to streamline that process. So I discovered that I could also make the SSHD a bash script. So it's a bash script and an ELF file at once. So the bash script that is embedded in the binary will take care of the change mod. We'll turn on the execute bit, then run it with the supplied arguments. So first, the privilege separation that I talk about. It's like will fork with for both two processes. One that is talking with the network, that is heavily restricted, change root with seccomp enforce, and the other privileged process, which is called the monitor. Most of the privileged process code is in the monitor.c file, and these two communicate over a defined protocol over a Unix socket. And it might surprise people, but the information that is sent and received over that socket is in the clear. So if you try to eavesdrop the network on the right side, the information is encrypted. But if you attempt to eavesdrop on the Unix socket that connect both the privileged and the unprivileged process, then you will have access to clear text credentials. So how it works is in the unprivileged process, the code will call request send to send data over the socket, and then the privileged process will receive that request with the credential, will validate, and will insert with insert old password to say if the account is authenticated or not after the password has been validated. But we can eavesdrop on that. You can test with the PS and the SS tools. So this screen capture has been made right after a client do connect, but before the user actually enter the password. So let's say you have root access on a machine, and from another machine you connect to it with SSH. You'll get the password prompt. You don't enter anything. You go back on your machine, and you use PS. You'll see the two SSHD child processes. The privileged one, you'll see priv within square brackets, and the network part of it, you'll see net into the square brackets. So you can get the PID 1360 for the privileged one and 1361 for the network code. And using the SS tool, you can enumerate Unix sockets that are used by these processes. So from the privilege size, the file descriptor of the socket is the file descriptor 6. And from the network side, it is file descriptor 4. So then you see the pipe that does link the two. And I made quite a few experiments. And if I monitor the privilege process to try to gather credential, I noticed that the file descriptor, which I can get them from, is pretty much always 6. Might be different, but in my experience, I got a lot of success with 6. So you can gather credential, like let's say overnight, over a few days, for as long as you want. And you can do it with strace if it's installed on the machine. You can also do it with other tools. There is a tool, it's called Tree Snake. It's like built-in wrote it, and that tool will extract password and show you the password automatically. But I prefer to use strace if it's already installed, and I will avoid to upload the binary on the machine. And the point is, your root already, it's like if you can't do that, that means that you already compromise that machine. But what you want to do is to collect and perhaps reuse credentials. So you wait for a system administrator to log in. So yeah, demo time. So it's this one. So I'm root already on the virtual machine. It's like the IP is 192.168.122.17, and then I look for the PID of the main SSHD daemon. So that's the one that is actually listening on port 22. Often you'll see, if you grep for SSHD, you'll see a lot of SSHD processes. You want to target that one that is listening to the main service port. So I'm running strace, and then I'm logging in as sysadmin. I use a long password. Passwords are getting longer and longer these days. So I'm typing the password in, and then as I hit enter, it generates a lot of logs files. So I grep for SSH connection to locate the file in which the credential will be logged. And when you find that string inside strace, the log file that will be generated by strace, you look for that string, and the password will be a few lines below. So here it is. So that's how one can abuse privilege separation of OpenSSH. So back to the slides. All right. So then I wanted to avoid the disk on the target side, and also avoid logging and login restriction. So I disable the no login check. So it's like there's a configuration file, you can deny access to some user in SSHD, so I disable that. So if my SSHD daemon runs on a server, even though that file is there and defined, I'll ignore it. And also, I'll always make sure the shell that you'll get is bin.sh. I wanted to use bash. I prefer bash, but I'm not sure bash is present on all systems, so I thought it was safer to use bin.sh. It's handy if the shell of the user that is compromised is, let's say, www data, and whose shell is no login. Like I said, the authorization is done with public keys, and the key is embedded in the binary. So I modified the make file, so when you build a project, it will generate a key pair, which I'll call ID Blackbear, and it will create a C file, pubkeys.c. We see it here, and it will embed the public key in a character array. Do notice the null pointer at the end. That is well tell my code to stop looking for keys. So you can add your own keys and rebuild, but make sure that null pointer is there. I did replace the usual code that is designed to read keys from authorized key file on disk with that function, read key file mem, which read keys from that array. So that's how authorization work with Blackbear. Also, the configuration of the SSH daemon is also embedded. You can modify it by editing servconf.c and recompile. So that's that way I don't have to rely on configuration file on the target side. And I also turn on, the gateway port option. When you use capital R to expose a port on the target side and to forward it on your side, usually by default you are restricted to the loopback interface. So you cannot, let's say your target as network interface and it will expose other network. You cannot serve a port to these networks. You can only serve to look back. So I turn gateway port on. So with Blackbear, you can expose port on all network interfaces on the remote system. Finally, the host keys are generated on the fly. That's a remnant of the whole design. So I didn't want to use host keys on disk. So I copied code from the SSH keygen. You know that part is responsible for generating key pairs that be host keys or user keys. So I copied the code responsible for key generation into the SSHD binary. But there's one big issue, is that you'll never know if the host key is good or not. So that makes the software vulnerable to man-in-the-middle attack. So I recently developed the code for compile time generation of user keys. So I should use the same code for host keys as well. That is a fix that is coming. And I wanted to deliver more effectively the binary. So I was tired of downloading. It's like, let's say you have a web shell, you have to send a request to download the binary, send a second request to turn on the executable bit, and then send a third request to run the binary with the arguments you want. So I wanted to streamline that process. So I found a way to include a bash script inside the ELF binary, sort of like the proof of concept or get the fuck out publication are doing with their magazines. It's like it's a polyglot file, or a file can be a multiple type at once. So I did look at the ELF header to find places where I could include my shell script. And if you try to, first I've tried to pipe my SSHD binary into bash, and then I noticed that it will fail, but later it's like it will go through the first 300 bytes, and it will fail at the first parenthesis it will encounter. So bash can actually is actually permissive, so you will absorb a lot of different bytes before it will bail out for a syntax error. So I did profit from that, and I also did profit from the fact that inside the ELF file header several bytes that are unused. So I use that small amount of space as a code cave to include a here document. So I used here document to make bash. When I pipe SSHD, I make it ignore whatever is between my here document inside the file header and the closing tag of the here document right before my script that I include as another character array. So we see here, I wrote a Python script that will patch SSHD to add the here document inside the ELF file header. And the lower part of the screen capture is in the reverse shell.c file. I added a character array which include the closing part, then the actual bash script that will receive arguments from the environment, and it will turn on the execute bit, then run the SSHD binary. So that is when the ELF takes over. So demo time. So let's say the program is compiled. I run the Python script to patch it, and then I'll move it to a location from which I will serve it to the network so the target can reach it. So I use a Python HTTP server to serve it. Then I will invoke the client. You'll notice I added the -r flag to specify a listen address, so that tells the client that I will need to listen for a connection instead of trying to make a connection. And also I included an example in the readme.md file that I will use against the web server. So I invoke the client. You have to specify the key, just as you will do usually. And I just made a mistake. I need to use -p. The regular -p will allow you to specify the port. So then the client is listening for a connection. I just copy and paste the command inside the damn vulnerable web application. And when I hit submit, I get a connect back. Then from there, the usual SSH protocol take place. So it's only reverse TCP, then it's regular SSH. So I'm www data. I can see my shell's user bin, no login, but I got bin sh. I can run top, I can run vim, and it's just like I had a regular SSH connection. So that's pretty much it. Any questions?